Alrighty. So, like I said, we have a cation for sodium, and we have an anion for chlorine. So, in this case, we lose that outer shell. So here's where that one electron was. So we kind of lose that outer shell. And because we have opposites attract going on here, they want to come together. So can you hear the music? That's the best part of the slide. I have music here. When the moon hits your eye like a big piece of pie. Alright. Alrighty, so yeah, that was the best part of the slide is the music. You're not the only one. I used this slide for another class that I teach at a different college, and they said the same thing. Even though I can hear it in my headsets, you guys can't hear it. And like I said, that was the best part of the slide, It only took me like 2 hours to do all the animation together, and it doesn't was like, no. Okay. Alright, so that's ionic bonds. Questions about ionic bonds at all? Alright, so the next one is covalent bonds. Okay, so now when we get to covalent bonds, what happens here is that neither atom wants to give up its outer shells at electrons. And those are usually those atoms that have 5, 6, electrons in their outer shells. They don't really want to give them up. They're sort of on the borderline. So you end up with these two atoms, and they both need more electrons in the outer shell. Neither one wants to give them up, and they sit there and go, well, why don't we share? So they're much nicer to each other than sometimes people are sometimes to each other. So there's no charges involved. And what we have here as an example is we have 2 oxygen atoms. So oxygen has 6 electrons in its outer shell. And truthfully, it wants to it wants 2 electrons, and it doesn't care how. So it can share them or it can gain them. It likes to share them more than anything else. So what we get here is they come together. Okay, come on, animations. Like I said, it's the best part of the slide. Okay, go. It must be there we go, and forward. And I kind of sit here, and I talk, and I fill in the gap, because the music is supposed to be doing this, and it's not. So, you see, now they're happy with each other because they're sharing these 2 atoms. So, and when they share, it's kind of like, they kind of do like both orbits. So you see electrons in the outer shells, and they're circling the outer orbits of both of them. Okay. And the music here was Caleb Scott. There goes my heart beating. So you are the reason. Anyways.
I love that song.
So that was our covalent bond. So just remember co means, working together, it means pairs. So it's real easy to remember that way. And then the last one we had that's mentioned in your textbook is hydrogen bond. I don't have real fancy animations for that, but hydrogen bonds are between hydrogen atoms and another atom. And essentially, a hydrogen atom has some weak polarity to it. So when we're talking about polarity, I found my real whiteboard, the one that I like to write on, so that I don't have any kind of weirdness here. So you have a hydrogen bond, hydrogen atom, like so. And basically you have this positively charged center here, but you only have this one lonely electron. And what it can do is it can cause some weak polarity. And polarity basically means, it's another way of saying charge. So this side of the atom that has the, electron closer will kind of have a negative charge, a little bit more of a negative pole there, because over here where there's no electron balancing it out over here, it sort of ends up with this kind of like positively charged side. And it's just that. So the biggest hydrogen bond that we have is water. So with water, we have our oxygen molecule. Okay, so now we kind of have this sort of negative side here, because we have these electrons. We sort of have this positive, weak positive. I mean, very, very, very weak, but just enough to be like, okay, maybe there's something there. So, and you get a hydrogen atom with this one little electrical charge. There's one little electron here that gives it kind of a weak negative charge there, and they sort of bond together. You got a positive and a negative. They're kind of a mix of both. They're bonded a little bit by those polarities, by those subtle charge influences, but they are also sharing that electron. So it's just, that's what I talk about, the electropositive hydrogen end of a polar covalent bond. It's just, they're kind of combining both. They get attracted because, there's this like little negative charge going, oh, there's this little positive thing over there. I'm going to grasp for anything positive in my life. I'm going to go for it. There's something positive there. Yes! And it goes over there, and, and then they're like, yeah, we can work this out. We can share this one electron, and that makes the oxygen happy, and that makes hydrogen happy, and, someday it'll be a Hallmark movie. So, okay, that's hydrogen bonds. We talk a little bit more about them when we talk about DNA molecules. So, questions about those? Alright, so let's kind of get into some more fun stuff here. So I'm trying to click on something else and I'm moving my slides here. But I talk about compounds and molecules. So we've talked about our basic atomic structure, and how we get positive and negative charges in our atoms, and isotopes and ions and things like that. Now we're kind of talking about some of the combinations that we see the most. So, different combinations, different ratios, we're going to form molecules, which are the smallest unit of compound. So, for instance, water, H2O, would be considered a molecule. That's a molecule of water. Okay, but, you get a glass of water, you get more there. You get something like oxygen. You always have two oxygens together, so that's a compound of oxygen. And you just have different molecules coming together, and they just start building upon each other. So when we have all these molecules put together, we have these chemical symbols and these formulas. And I'm just going to jump to the next slide because this kind of helps explain it a little bit more. But here we have a compound. We got carbon, hydrogen, and oxygen. So in this case, we have 6 carbons and 12 hydrogens and 6 oxygens. And it's coming all together to form, that's basically a glucose molecule. That's your energy source for the body. And then we have oxygen, O2, which is a molecule of oxygen. We got 6 of those. And now we're going to produce carbon dioxide and water. So molecules are just basically like just very simple combinations, and then when different molecules come together to create more, then we're starting to get into compounds. So it's a little bit like, 2 is company, but 3 is a crowd. You get a couple molecules together, and that's not so bad, but then you start adding 3, and the next thing you know, you got 4, 5, 6, and now you're getting very complex and you're getting into a compound. Okay, so questions about that? Yeah, so we go hierarchy. We go atom, element, molecule, compound. It's kind of, we keep building one after another. Okay. So how we build those together, though, are the basis for chemical reactions. So this is one that's listed in your textbook. So like I said, this is glucose, which is a sugar, and oxygen, which we breathe in. And it breaks down into carbon dioxide and water. So what we have here is basically a simple chemical equation, which starts on get my annotations going here, starts on the left side with the reactants, and then on the right side we have the products. And the arrow is the connector between the two. Okay. So one of the things that you'll notice is that if you were to sit here and count them, because I know you guys just have so much time in your day and you want to do this, but if you count the number of carbons on this side, you have the same number of carbons on that side. And you have the same number of hydrogens on this side as you have on that side, and so on and so forth. So that's the thing about chemical reactions with reactants and products, is that what goes in the atoms that go in come out. They combine in different forms because they've reacted with each other to make a new product. But you don't have a situation where you do when you get into organic chemistry, but we're not going to go there. But you throw in, like I said, this glucose molecule, and then all of a sudden you're not going to have a product of something that we didn't start with. Like, you're not going to have a nitrogen over here, because we have carbon, hydrogen, and oxygen. Carbon, hydrogen, oxygen. You're not going to have nitrogen come out. Okay? Not in this sense. And this is an oversimplification. So if you've taken classes and you're like, Miss Steinsultz, that's not true. Yeah, but for our purposes, what goes in, the number of atoms that go in is the number of atoms that comes out. It's just recombined. So just remember that for our purposes, we're doing a overview and oversimplification. Okay, I'm starting to see a trend here, is that when I start using the text box, even though it was doing just fine to me, a minute ago, it starts freezing things up. But I did get a question in the chat. At what number do molecules become a compound? There's no set number for that, for anything. It's just basically, it depends on the compound. So it's not like all of a sudden, okay, if we get 3, it's a compound. It's basically, compounds and molecules are kind of used interchangeably. There's really no set number per se. Like, you get 4 compounds together, now you have a molecule. 4 molecules together, now you have a compound. Just as you keep building, eventually it gets big enough where it becomes a compound, or it gets complex enough where it becomes a compound. This is water, but it's not really what I would call a compound because it's just water. Okay? But if I were to bring a bottle of Coke in here, I would call Coke a compound because it's got a lot of stuff in it. So it's that. Does that help answer your question, I hope? So, let me see if I can get this going again without losing you, and then I will know not to it's doing it to me again. It completely freezing up everything. It's not letting me forward or back anything. Let's try me. Won't let me out. Okay. There we go. I'm going to try and clear. Does not let me do that, but I found kind of a trick here. Try this. Something to do with the annotations that's doing it, so. Okay. The good news is I have somewhat of a workaround. The bad news is we're going to have the words reactants and products in our slides for the rest of the day. So, except when we switch over to the other slides. Alright, so different types of reactions that they describe here. The first reaction that we describe in a textbook is your synthesis reactions, which are really your simple ones. You take two things, you put them together, you get a third. These are they're very simple. Just a couple of atoms, you put them together, you get some type of product. So you put sodium and chloride together and you get table salt. You get two hydrogens and an oxygen together, you get water. These are just really simple, A plus B equals C and kind of reactions. And those are the simplest ones. And a lot of what we're going to talk about in this class, if we do talk about any reactions, are going to be more along the lines of synthesis reactions. Because, it's not an organic chemistry class, so it doesn't need to go into that deep. But the other type of reaction is called a decomposition reaction. So this is where you have your main product, and it breaks apart into something. So hydrogen peroxide comes in those brown bottles. You don't want to expose it to light because it will break down into plain old water and oxygen. So that's kind of a decomposition reaction. You could call rust, in a sense, rust on your vehicle is kind of a decomposition reaction because it's breaking down the metal in the body of your car. So that's kind of a decomposition reaction going on there. And then we have double plate replacement reactions. And this is where you kind of you got two items here. So in this case, we have sodium hydroxide, NaOH is sodium hydroxide. Don't get hung up too much on what these are. Just kind of note how things switch. You put sodium hydroxide plus hydrochloric acid together, and you're going to get common table salt in water. So it's kind of like sodium hydroxide and hydrochloric acid go on a double date, and then they go home with each other's person. It's kind of a double replacement there. You're like, you and your best friend. Your best friend sets you up with somebody, and you set your best friend up with somebody, and you get to the table and you realize, no, I like the other guy better, or whatever, and yeah. So that's what we got here. We kind of got a double replacement going on here. So, that's what that is. And then you have your exergonic and endergonic reactions, which release exergonic reactions release energy. So they release heat, and endergonic reactions require an input of energy. So trying to think of a good exergonic reaction that releases heat off the top of my head real quick. You ever tried to, did you or maybe your kids ever try to build a volcano before, and you put a little, what is it, baking powder or something in there, and you mixed it with something else and it tries to foam up and bubble, and you get a little bit of heat from that? Kind of got yourself a minor little exergonic reaction going on there. A better one, here's one for you to try at home out in the backyard, but I don't know if you've seen this yet, but take a big 2-liter of soda, one that's fresh, and drop a Mentos into it, and the soda will come shooting out like that. So do it in the backyard. That's sort of a little bit of, it's not really an exergonic reaction, but it's kind of like gives that aura of one, because it causes the soda to go shooting straight up in the air. It's a lot of fun. So if you have kids, they would really enjoy that. And then endergonic reactions are ones that require an input of energy. So endergonics, you need energy to make this happen, and exergonic is going to release it usually as heat. The only other two that were kind of mentioned in your textbook are also the endocytosis and exocytosis as well. So exergonic reactions, here's one. ATP, which is a molecule, a compound actually, I should say, that your body uses for energy, adenosine triphosphate. Add that with water, and then that'll break down into ADP, adenosine diphosphate, plus a lonely phosphate, but it releases energy. So without ATP, I can't do this. I can't raise the roof or, do the Arsenio or whatever. So I can't do any of that. But an example of an endergonic reaction is photosynthesis. So this is what happens in plants is they take carbon dioxide that we breathe out. The plants take it in, throw a little water in there, a little photosynthesis from the sun to give it an input of energy, and next thing you know is you have glucose and then the oxygen, which the plant will release to the environment for us to breathe in. So we need to be nice to our plants because they provide us oxygen. All right, how's everybody doing so far? Hanging in there? Okay. I kind of completely frozen up. So unfortunately, I can see Brent, Eleanor, Aaron, Taylor, and Brianna. So the rest of you, it's not that I don't like you, it's that it's not letting me see the next group. So if you have questions or anything like that, hit up the chat box. And then when we get to the end of this PowerPoint, which is I think we got about another 15-20 minutes here. Most of what we were going to do today was this first one. We'll take a break, reboot again, and then I just won't use the annotations for the rest of the time here. I'll use my trusty little whiteboard here. So with those basic types of chemical reactions, there are different things that are going to influence how much those happen. And the big 5 factors are listed here is the nature of the reacting substances. Some substances just have a tendency to be more volatile than others. It's just the nature of how the substance is built. For instance, if you got brothers and sisters, you probably have, Brett's got a kitty cat. If you got brothers and sisters, you might have one that flies off the handle a little easier than maybe the rest of you guys. Or if you have kids, you're like, okay, this one is my temper kid, this one is my calm kid. It's just the nature of them. It's the nature of the substances. So some are more reactive than others. The temperature. So as you increase the temperature of anything, what happens is when you increase temperature, is you're causing the molecules and the atoms and all that in here, you're causing them to move around a lot more. And when you cause them to move around a lot more, they're more likely to react. So if we all know this, we've seen in movies, two alpha males get together and they start yelling at each other, and the chances of them getting actually into a fight is if one gets shoved into the other one, right? Then, kaboom, everything starts happening. So the same thing there. Concentration. If you've got a lot of it, you have more opportunities for reactions. So if you've got a huge concentration of it, more opportunities for reactions. And then we have enzymes or catalysts. So enzymes and catalysts are things that we can use to speed up a reaction. But they don't really, at the end of everything, they don't combine with, so you have your reactants, you have your products, you throw a catalyst in there, and the catalyst doesn't combine with the product. It stays alone, but it will get the two reactants to go a little faster. So a lot of times, we'll learn this in a Krebs cycle. There's a lot of different enzymes in there. I'm trying to think of one. The only thing I can think of is heat, which is not at the point. So let my mind think about that for a minute. If I remember, I'll get back to you. And then surface area. So the more surface area we have for something to react with, the more opportunities we're going to have for a reaction. So, and this can be thought of like if you're barbecuing in a backyard and you're using charcoal. If that's all kind of pounded down into a briquette, into a little square of charcoal, and you just light that square on the outside, you'll get a nice controlled reaction. But if you were to take that, and do not try this at home. Do not try this at home. But if it disintegrates and then you put it, don't do it. I've never tried it. I'm sure there's a YouTube video somewhere. But it's just because you're increasing the surface area for that, you can get a bigger reaction from that. So your surface area does that as well. Okay. So kind of going back to that, when we talk about the reaction that put people together, a mixture can be something as two or more substances. So here's a couple more definitions for you. A mixture is two or more substances that can be separated out. So if you think of like, for instance, soda pop. I used to do this experiment in college. You can actually extract the caffeine from soda and put it into a powder form. So you can separate these things out. Solutions are things that a solute, which is usually water. Water is a universal solvent. So we have a solute, which is our particles, being dissolved in our solvent, which is water. So when you're making Kool-Aid or lemonade or anything like that, you put your powder in here and you're shaking it up. Your Kool-Aid is your solute and your water is your solvent. You shake it all up and it dissolves nicely into here. And then colloidal suspensions are important in our field because the barium that we have our patients drink is a colloidal suspension. The particles never really, they don't dissolve in there, they sort of remain suspended. And I'm actually going to grab one. I did an experiment yesterday in prep for this. I'll be right back. I'm going to go grab it. Sure, you guys are all like, what is this brown water she's showing us? Okay, so it's a little experiment that I did yesterday, but this is water and this is cocoa powder. You can see on the very bottom, the cocoa powder has kind of layered out. So you do still have some in here, but it's basically sort of suspended in it. It's also kind of layered out at the top a little bit too. So this is a colloidal suspension. It's not dissolving in here. It's just sort of floating around. But do this, it's nice and dark again. So, and then if I set it in 24 hours, it will look like what it just looked like before. So I lost all of my cocoa powder. So that's a colloidal suspension. So when James Bond says shaken, not stirred, he's really just trying to, mix up a colloidal suspension for his martini. So that's there's science behind that. I don't know alcohol, so. Alrighty. How's everybody doing? Yeah, hang in there, guys. Okay, so the last part we're going to talk about today are some acids, bases, and buffers. And then we'll talk a little bit about some organic compounds. We'll take a break, and then we'll jump into chapter 3, which is cell structure and function, which won't take us nearly as long as, hey, we're back in business again. So it won't take us nearly as long to do. We're at 2:25, so we're going to go till 4. Alrighty. And I don't know why it all of a sudden did that to me, but I'm freezing up again. So let's see here. What I'm going to do is. If I could get to the next slide, that would be great, because now it's not even letting me get to the next slide again. Okay, I might have to do a reboot here, folks, because it's just not letting me do anything. Alright, time for another 5-minute break. I'm going to have to reboot, guys. I apologize. I'm having so much trouble with this, but, it seems like it's a Zoom thing, because I haven't had any trouble with this from my house thus far. So, alright, just take a quick 5-minute break, get something to drink, and I'll be right back.